Hey, good afternoon, everybody. Thanks for understanding about our different class format today. I'm at my parents' house, and they're sick, and I'm helping take care of them. So this will be just a video that goes through some of our information and has a lab at the end I'd like you guys to do. And then I will post the homework in Slack. Hopefully I'll see you next week. I slept with a heater blowing on me to keep warm. Because it was a little cool in the house, and it has definitely affected my voice. So I'm going to sound a little weird for this video, but we'll make it through. Okay. Okay, here we go. So we're going to talk about mountain formations and 4 different ways that they are formed. The book just talks about 3, but we're going to add on 1. This is a handout that you will need. It is in Slack. You'll need to print it and have it for the rest of this video. If you don't have it, then I would suggest pausing the video right now and printing it off and then coming back. If for some reason you're not able to print at home, this is a pretty simple graph. If you just want to have mountain type and then how they form, then I can have a few printed off the next time I see you, and you can put that information in with the pictures. I don't expect you to draw the pictures if you can't print it, but if there's any way for you to print this off first, that would be great. And you can fill it in as we go. Okay, are there any mountain ranges where we live, and how did they get there? We don't have mountain ranges technically in Missouri. We do talk about the Ozark Mountains. They're not technically high enough to have that specific mountain title, but some of those hills and things would be formed in similar ways as a mountain range that's taller. So in the United States, though, we do have, it's a little hard to see on this picture, but the Rocky Mountains and Smoky Mountains, Appalachian Mountains. So formation of mountains is orogenesis, and just to be a little bit of a word geek, orogeny means mountain in Greek, and Genesis is just like Genesis in the Bible. It's like the beginning. So 4 types. These 4 are on your worksheet: folding, fault block, volcanic activity, and dome. You don't have to write anything yet. So there they all are. All right, the first one, folding mountains, and this picture matches what's on your worksheet. In fold mountains, the rock layers are compressed, and the way they are formed is when 2 plates collide. And you can see in this is showing the plates moving towards each other. And we talked about how when plates move toward each other, it is a convergent boundary when they move toward each other. And this can form a fold mountain. It's like the earth just sort of folds up from the level of the crust. So here's one way that it can happen. Here's your 2 plates moving toward each other. Sometimes this is a continental crust. Sometimes this could be an ocean crust here. But when one crust goes under the other, it's called subduction. And you'll get these fold in mountains. And sometimes there could be, especially in the ocean, there could be a trench form right here or a depression. So when one crust goes under the other, that is called subduction. And that's one way that fold mountains are formed. And sometimes one does not go under the other, and they just bump up. I don't know why that helicopter's there. And they form these folds. And what you'll see is if they were able to cut into the mountain, they would see different sediment rock layers inside the mountain, especially right in this area, they would see the different layers. All right, so we're going to look, there's a video. That is a neat experiment. A French man made a model out of sand. Here we go.
How do mountains form? We see them in just a moment of time, but they form over millions of years. Mountain belts extend for hundreds, even thousands of kilometers, and their structures penetrate deep into the earth. So their size and age make their formation difficult to understand. French geologist Jacques Malavier builds sand models that mimic the formation of mountain belts and allow scientists to study this complex process.
In order for an experiment that runs for only a few minutes but represents natural phenomena that happen over many tens of millions of years, we have to choose a material whose deformation behavior does not depend on time. Sand is a very good material for simulating rock deformation. In the experiment, the different stratigraphic layers which represent the sediments and the continental crust have different mechanical properties. We mix the sand grains with a finer powder, which increases the sand's resistance to deformation. Thus, we have heterogeneous material made up of more resistant layers and less resistant layers.
Mountain belts are created when continents collide. In this experiment, we see two continents separated by an ocean. Now watch what happens as the plates converge. As one plate subducts or dives beneath the other, the ocean basin closes. The continental crust, which is lighter than oceanic crust, cannot be subducted. Instead, as the continents collide, the crust thickens and is forced up. Note how the sand is folded and faulted. We see similar structures in the rocks in mountains. One important factor not accounted for in this model is erosion. Erosion exposes the deformed rocks that were once deeply buried in the mountain belt. The green sand represents the rocks of the ocean basin. Note that it's been trapped between the two continents, marking their original boundary. These too we see in mountain belts. It's very difficult to understand the deep structure of a mountain belt by direct observation. The sand model allows us to compress time and space and simulates the internal structure of mountains.
Yes, I really like that model because you could see all the sediment layers. So that was fold mountains. This is the information you would need for your worksheet. This picture is fold mountains, and they form when two plates collide. If you need to pause for a moment to finish filling that out, then please do so. Okay, the next one we're going to talk about is fault block mountains. Fault block mountains are made from rocks that are separated from each other by faults. Separated by faults. And this is a fault, basically a crack in the earth. And sometimes they upheave like this, and sometimes it's a little more, not quite as slanted, but let's take a look at how that might form. So in this case is two plates moving away from each other, so a divergent boundary, and those plates moving away can cause these tension cracks or faults in the crust. And at that fault line, then the middle in between can sink, and that can form a mountain on each side. So this image shows it sinking like straight down really and forming this really straight-sided mountain. And this could happen multiple places, so you could have a whole mountain range. And then sometimes in this area here, you'll get like erosion and sediment buildup so that the side of the mountain is not so straight up and down. And so the tall region are called horsts, and the lower regions are called grabens. And then these are all of your fault lines that occurred from the plates moving away or divergent boundary. So this is our first slide again. So fault block mountain goes with this picture. And you can just copy this right here. They're made of rocks. You can start here. Rocks that are separated from surrounding rock by faults. Or you could even say fault lines if you wanted. Okay, and this is a picture of the Teton Mountains in Wyoming, which are fault block mountains. When you look this up, they're always showing you pictures of mountains. I honestly do not know how they tell just by looking at a mountain that's been around for so long and a lot of erosion has occurred, how they can tell that it is a fault block mountain or a fold mountain, but they could potentially tell if enough erosion had occurred, they could see the different layers and how they were organized. Sorry, I keep losing my mouse. Okay, the third, and I'm jumping ahead a little of what you read, but a third way is volcanic activity. So volcanic mountains form when lava or molten materials, it's not lava till it reaches the surface, molten material reaches the surface through a weak area of the crust and then, bursts out. And it says most of them occur in the Ring of Fire. 75% of the volcanic activity occur in the Ring of Fire, which also means that there's also a lot of plate boundaries in this area. And so those areas are prone not only to volcanoes, but also earthquakes. And so you're saying, what is the Ring of Fire? We will talk about this more when we talk about volcanoes. But basically, if you look at this map, this area has the most amount of volcanic activity and plate boundary movement. And so it's really more of a horseshoe than a ring, but they call it the Ring of Fire. And you see in North America here we have California, is known. They're on the coast for earthquakes, and so they're right on a plate boundary here. So that is the Ring of Fire. We'll get more information about that later, next week or so. So that is the volcanic mountain. So when the type of mountain, it was a volcanic mountain, and the way it is formed is when molten material reaches the surface through a weak area of the crust. Give you a moment to write that down. Hit pause if you need to. Okay. Dome mountains. Dome mountains were not mentioned in the book, but it's just basically a volcano that didn't bust through. So there is a picture for this on your little worksheet. So dome mountains form when less dense magma beneath Earth's crust are pushed upward. So it wasn't dense enough to break through, or the crust wasn't weak enough. So the lava never reaches the surface. So it is a dome mountain formed when less dense magma beneath Earth's crust are pushed forward. So you can go ahead and pause if you need to write that on your sheet. So I'm just showing you this again. So each of these should have been filled out already. This is a fold mountain, fault block, volcanic mountain, or dome mountain. Okay. Now, at the bottom of your worksheet, see over here, there's a spot that says additional notes. So what we want to do in this area is we want to add another mountain. That was in your book. It's called a plateau. Plateau, that's how you spell it. And I would like you to draw a picture of it. This is a picture right here. A plateau is basically a mountain that is flat on the top. So pause for just a moment and write plateau and draw a picture. And once you're ready, hit play again, and then we're going to watch a short video on how plateaus are formed. Here we go.
In this video, we're going to learn how plateaus are formed. A plateau is a flat, elevated piece of land that is higher to the surrounding land area. There are two kinds of plateaus, dissected plateaus and volcanic plateaus. Dissected plateaus look like this. These are formed due to upward movement in the earth crust. One side of this plateau will have a slope. Basically, when two continental plates collide, that is how mountains are formed, right? Even plateaus are like mountains, except it has a flat top. So even dissected plateau is formed due to slow collision of tectonic plates. A good example is the Colorado Plateau in US, Tibetan Plateau, Mexican Plateau, and Patagonia Plateau. And the second one is volcanic plateaus. They are formed by numerous small volcanic eruptions that slowly build up over time, forming a plateau. We already know that a plateau is an elevated piece of land. When lava continuously flows out of a volcano, with time, lava gets accumulated in the form of layers. And that is another way plateaus are formed. Some examples of volcanic plateaus are the Columbia Plateau in the northwestern United States, the northern islands of New Zealand. In India, Malwa Plateau and Deccan Plateau is of volcanic origin. Now, erosion due to wind, rainfall and rivers can influence the shape of a plateau. Even in the oceans, you will find plateaus. Oceanic plateaus are of two types. One is made of continental crust and the other is made of igneous rock due to solidification of lava.
Okay, so at the bottom where you drew your picture, it said plateau. Plateaus are formed by plates, continental plates colliding slowly, so more slowly than, let's say, a fold mountain. So that's why you don't end up with this upheavaled, pointed top. And then the buildup of lava. So once again, that lava is flowing slowly. It's not this huge spewing volcanic eruption. It's a slow release of lava that builds up over time. So those are the two things that should be for how a plateau is formed. Pause if you need to. Put that at the bottom of that note sheet. So just a little review. Two plates that come together that are moving towards each other are called convergent boundaries. Plates that are moving away from each other are called divergent boundaries. And then the other boundary type is called transform, and they are moving sort of parallel to each other. And this is called, this is a fault line. It's just kind of a picture that shows them moving parallel to each other. It's called a slip fault because they're sort of slipping by. And your book kind of talks about if these plates are moving all the time, then why don't we feel it right now? Well, sometimes we don't because they're moving slowly enough or they're smooth enough. Plates are moving maybe 10 centimeters in a year. If you get a ruler and see how far that is, it's not very far. But of course, they're not smooth, so they're going to catch on each other. And that's how an earthquake might happen. Also, even though these two plates are moving next to each other, so it's not going to have this big upheaval of mountain, it's never smooth. So there's going to be some kind of disturbance of the crust. And here's an example. This is the San Andreas Fault, and you can see the fault line itself. This is going to move next to each other. And there's some upheaval of crust. It's not a huge mountain range, but it's not flat anymore either. So that can also form some kind of upheaval of the crust. And that was from a transform boundary. So, I just got ahead of myself a little. So with the earthquakes, right, so they're moving slowly, like 10 centimeters a year. So we don't feel them all the time. Now, some earthquakes happen closer to the surface than others, and so we might feel them more that way. Also, sometimes they might catch on each other, and there'll be a pressure buildup before the plates separate, and that's going to give us a higher magnitude of earthquake. So that's the word that they use to determine how much of an earthquake we feel, magnitude. And then the plates moving could cause cracks in the crust called faults, which we saw with the fault block mountain model. And those faults can move too. So here's a scale of earthquake magnitude. So if it's 2.5 or less, we're probably not going to feel it. 2.5 to 5.4 is felt, but only causes a little bit of damage. And then the higher the number, of course, the greater the damage and the much more we're going to feel. Now, how do they measure this? We will talk about that after we learn about seismic waves. So you haven't read about that yet, so we'll explore that a little more in the next few lessons. Okay, this is the last thing I want to talk about. Short video today. So I would like you to try to do this lab 3.2.2a earthquake energy at home. You need a desk or a table. You'll need some masking tape, a cup of some kind. You do not need sand. This says sand right here. You don't need sand. You do need a rubber band and a tape measure and a friend, family member. So do this along with your friends. So you're going to put this cup. It says fill a large disposable cup with 50 grains of sand. Oh my gosh, don't do sand. So the object of this is you might potentially knock that cup over. So 50 grams is just a couple of ounces. You could put water in the bottom of your cup. You might try just a water bottle with a little bit of water in the bottom. What you want is you want something that could knock over fairly easily, but that won't just fall over when you walk by, with the wind of your body walking by. So I'm just wanting a little bit of weight in the bottom. So I'm going to let you guys figure out what might work for that. And if you try something and it doesn't work, try something else. Okay, so you're going to set the cup on the edge of the desk, and it's as closest to the chalk line. So I would put a piece of tape, or if you have carpet, just make sure you're measuring out 2 meters, which a meter is about a yard. So if you'd like to go 2 yards away, this is 2 meters, 2 yards is fine, from the edge of your table at home, and mark that with some masking tape so you can stand there. You're going to put the cup at the edge, and then you're going to basically shoot at it with your rubber band. But you want to make sure you're stretching the rubber band the same distance each time. So number 4 here, that's why you're measuring how far you're stretching so that you can stretch it the same way the next time. My mouse keeps disappearing. And this part that says aligned with the edge of the desk, you're not touching the desk. You're just not shooting at it while standing up. You're going to have to bend down so that you're at eye level with the desk. And then you're just going to try to shoot at the cup. And then you're going to move back and shoot at it again. Now, if you miss completely, try again. You're trying to hit the cup. Replace the cup, any stuff that falls out of it. I was thinking you could even throw like a couple marbles in there or something. And then you're going to keep increasing the distance, and you're going to record the distance that it moved and the length of the stretched rubber band. I don't know why you're doing the length each time, because you're trying to do the same length every time. but the length will be different for each of you depending on the rubber band you have. Once you've completed this, and please message me in Slack if you have any questions, especially shoot me a photo and say, am I doing this right? I'm happy to answer. There's also some questions and a chart, a graph on the back that you need to complete. Okay, and I think that's all I have to say. That is it. Thank you very much, and have a good week, and I will touch base with you. Hang on to your review questions, and I will just check them all next week. Okay, bye, guys.